Hey, what's up YouTube? Today we're going to be talking about motion along a curve. So, let's get right into it. First, before we get into actually discussing motion and representing it in terms of derivatives and using calculus to solve problems with motion along a curve, first we have to talk about the concept of a vector. And a vector is something with a magnitude and a direction versus something called a scalar, which just has a magnitude. So, vectors are represented by lines. So, let's draw this here. If I say, for example, I have 5 units of whatever going in the northeast direction, that becomes a vector. Whereas if I just said I had 5 units, that doesn't have a direction. It could go anywhere, it could go nowhere. That would be a scalar. The distinction here is important because we need to know that in terms of the difference between velocity and speed. So, velocity starts with a v, so that's a vector. At least that's the way you remember it. And speed starts with an s, so that is a scalar, because that also starts with an s, just as an easy way of remembering it. Speed does not depend on direction. I could be going at 10 miles per hour, but it doesn't matter in what direction I'm going. For velocity, it's speed plus direction, meaning that I would be going 10 miles per hour north, or in some sort of direction like that. So let's talk about motion. Motion with respect to time can be represented by x of t or y of t, either way, but we're just going to focus on x of t right now for just for sake of simplicity. So let's say I have a graph here. This is x and this is t. I could represent the distance from the origin as time moves forward. Distance could be further, shorter, whatever. As it goes up, it's further away. As it comes closer, it's shorter, etc., etc. Now, the velocity is the direction and the speed that it is going in, meaning how fast is the distance changing with respect to time. So we can say, let's just start off with average velocity. So the average velocity, the average change in velocity, is going to be equal to delta x over delta t by definition. So we could also represent this as the function x of t plus delta t plus that change in time minus x of t, which is just the initial time. So x of t final minus x of t initial over delta t. As you can see, they're the same way of writing that, but as you can see, this is something you should be familiar with. This is the structure of the derivative. If we just replace this with h, it's exactly the same. So this brings up the concept of an instantaneous velocity vector. So the instantaneous velocity will tell us the magnitude and direction at a specific point in time. So that would be the limit as delta t approaches 0. And if we understand that, then we understand that we have this is where the derivative comes from. So I'm just going to write this here to symbolize that this is the same thing. And what we end up with is that this is the derivative of distance x over t over dt. So velocity is the derivative of x with respect to time. And now, in that strain of thought, acceleration by definition is the change of velocity with respect to time. So the important thing here, since now we're doing calculus, is instantaneous acceleration. The instantaneous acceleration is going to be the derivative of velocity with respect to time. But if the derivative of velocity, or if velocity is equal to the derivative of x with respect to time, then the derivative of the derivative would be the second derivative. So acceleration is also equal to the second derivative of x with respect to time. Should be simple enough. So now that we understand that, let's go in deeper into the concept of velocity and acceleration and what's going to be important on the AP test or any sort of problems you get relating to these problems. And it's mainly in conceptualizing what a vector means. So if the velocity is greater than 0, as in if it's positive along this axis, that means that the particle is moving in the positive direction. If the velocity was negative, that means it's moving in the negative direction, as in backwards. Now, if acceleration is positive, that means that velocity is sort of increasing in this direction. It could be moving in any way, but what that means is that if it's going in this direction, it's moving towards the right, so it's slowing down. But if it's moving in this direction and it's moving further in this direction, it's accelerating in that direction, it's speeding up. Whereas, if the acceleration was in this direction, as in if it was negative, it would be moving towards this direction. So, this over here, if it's moving in the negative direction with the negative acceleration, it's speeding up in the negative direction. Whereas if it's moving in this direction, but it's accelerating in this direction, they're accelerating in opposite ways, or moving in opposite ways, so it's actually slowing down. And so, what we get here is that speed only increases when velocity and acceleration have the same sign. When they have different signs, the speed will actually be decreasing, even if the velocity is increasing or decreasing. That just depends on whether velocity is negative or positive. So now let's move on to the last or second to last part of this, which would just be parametrically defined ones. So this one is going to be important for mainly the BC test, but it could be useful to know anyway. And this usually occurs when we have velocity that's moving in two directions, and I'm going to start off with explaining why this is important to know. And that will be concerning parabolic motion. So we want to describe motion, but obviously motion doesn't always move along in one direction. Motion moves along in multiple directions. So I launch a football, football season's starting tomorrow. I launch a football, because the Broncos and the Panthers are playing, right? And it moves in sort of a parabola, and some sort of parabolic motion, right? So if we go and zoom in over here, this vector looks like this. So we want to split it up into its two components. It has a y component, as in it's moving up, and it's an x component, as in it's moving to the side. Now, the physics of this is also important, but that's not important for this lesson specifically. So that means that there's a velocity in this direction and a velocity in that direction. So the velocity will actually be the vector sum of dy over dt plus dx over dt. Now this should be a quick review of derivatives that are parametrically defined, but if we wanted to find dx over dy, then we could use our knowledge of fractions to find that, because this would just be, oh, my bad, dy over dx, not, yeah, here, dy over dx, not dx over dt. So use our knowledge of fractions and just cancel out the t. So we have over dt over dx over dt. And then the dt's will cancel out, and what you are left up with is dy over dt. Obviously, you don't just cancel them out. You have to actually take the derivatives and then divide them, but that's what you get there. Now let's say you wanted to find the magnitude of this, right? This tells you the direction and the magnitudes in each direction. But let's say you just wanted to find the magnitude. Obviously, this can be rewritten as a triangle. This is how you do vector sums, by the way. You apply this to this end over here, right? So we call this the head-to-tail method. So we have vector 1 over here. This is the x1. And then we apply this vector over here. These are the two vectors we're summing, the x and the y. And then we connect them like this with this vector that we're trying to find the sum of. And as you can see, this is a right triangle. So what we end up with is, the radical. This is just a Pythagorean theorem, so you just want to find the length of that. So what you end up with is dy over dt squared plus dx over dt squared, and then you have the radical of that entire thing. And what we notice is that this is the same exact thing as acceleration. Acceleration is represented in the same exact fashion, has acceleration in two directions at times, although in this case actually we'd only have acceleration in one direction, but that's unimportant. Let's say it had acceleration in two directions. What you'd have is acceleration is, and I'm going to represent it by its second derivative, because that's what is most commonly represented as. So we have two directions, right? We have dx over d2x over dt squared, and then we have that plus, or usually this is a comma actually, but whatever. d2y over dt squared. And then if you wanted to find the average acceleration using these derivatives, you could find d2y over d2x, but that's probably not something you're going to do. You don't have to worry about that. Now, here we have this average acceleration being equal to basically the sum of the radical of the sum of these squares. So the radical of the squares of these second derivatives being added together. So d2x over dt squared squared plus d2y over dt squared squared. And then you take the radical of that entire thing. And then you end up with the acceleration's length. And that covers motion along a curve. But before we go, let's just quickly talk about 3D analysis. So this will just be some notation. Usually when you represent a vector, you're going to represent it along a plane of 3 curves, meaning that you're going to have, as you can see, some sort of box. Remember, we work in 3 dimensions in real life, not 2 dimensions. So this is our y, this is our x, and then we have this additional 1z. So we say this as some unit x, some distance x in the I hat direction, plus some distance y in the, now this will be the j hat direction, and then plus some distance z in the k hat direction. So I, j, and k are just the directions. This is something that's just a side note. I don't think you need to know for the AP, but it's good to know for vectors. I hope you enjoyed this video. Please give it a thumbs up and subscribe. And if you want more, I will see you tomorrow.